on this computer. This exam will take place on Monday. Hopefully you've taken a look at the practice exam. So let's go ahead and I will, let's see, I want screen 1. Okay, everybody can see this screen. Oh, it's not my pen. All right, so here's the practice exam I wrote, and there's some hints about what will be on the exam in the future. So let's go ahead and see. So it will be electronic. So a lot of these questions so this first page will probably be on the exam. It will be multiple choice as opposed to write in your the thing that I'm expecting. So let's go ahead and go over this. So which of these following data structures, array list, linked list, stack, queue, tree, priority queue, set, or map is best for the example given? You need to model which patient should be seen next in the hospital. Patients should be seen in as close to order of arrival, but patients in a more severe situation should be seen first. What data structure would be best for keeping track of your patients in that case?
Priority queue?
Yep, a priority queue, right? Yeah, I know, topical. All right, a router needs to hold a buffer and deal with packets in the order that they appear. What data structure is that?
Queue.
Yep. Which is spelled Q-U-E-U-E, and it's pronounced the first letter and ignore all the rest. Right? So you need to model a hierarchy. What data structure is best for modeling any kind of hierarchy?
Trees.
Yep, trees. If it's a hierarchical data structure, you want if it's a hierarchical information, you want a tree. All right. You need a data structure to hold your previous decision in case you need to backtrack. Which is best suited for this?
Stack.
Yep, stacks are all about backtracking. All right. Answer the following vocabulary questions. The node at the top of the tree is called what?
Root.
Yep, it's called the root. Links from a node to its successors are called what?
Edges?
Edges. You can also call them links because I use that. I know it's one of those axiomatic terms. You can also call them branches if you really want to. So the predecessors of a node in a tree is called its what? What is the direct predecessor called?
Direct child.
Predecessor.
The parent?
Yes. Parent.
And the last question, would pointer be an acceptable answer?
Would what?
Pointer?
Yeah, I would take pointer as well. I mean, the point is that there really aren't wrong answers for that, because so long as they make sense and work in this. Nodes that have the same parent are called what? So this one we never really went over, but
Siblings?
Nodes that have the same parent. Yes, but I have to say that they are siblings. And now, what would you call your parent's sibling? Any ideas?
Uncle?
Yep, you can call it yep, that's pretty much the term we use, aunt or uncle node. All right, so let's describe, without using code, how to calculate the height of a tree recursively. All right, so how? You're broke? Oh, you pooped. Oh no.
Come on down, I'll help you. Come on down.
One of the students said, me too. Oh, never mind. All right, so let's go ahead and so how do we use how do we get the height of a tree recursively? Well, the height is the number of nodes from here to the bottom level, right? So let's go ahead and open up a whiteboard, right? And let's see how well I can do this without a pen, right? So let's go ahead and draw here. Use this, right? Okay, this works just fine. So the height of this tree is 2. Now we add a node to it. It is 3. And now at this point, the height of the tree is 4, right? Now, some mathematicians might tell you, so I go with the node count for the height. Some people go with the edge count for the height. So they would say the height of this tree is 3, but that's honestly a moot point. I prefer going with the height of the node being this. So how do you figure it out? Well, you figure out your height. How would I figure it out recursively? So if I don't know how big the tree is, right? When we think about it recursively, we think about it in terms of like, here is my node, here I am, and here's my left subtree, here's my right subtree, right? So I think to myself, well, I know that I must be at least 1, right? So my total height would be 1 plus however big my left subtree, however high my left subtree is, or however big my right subtree is, whichever is greater. That makes sense? So it's 1 plus the height of the bigger of my left or right subtree. Make sense to everybody there?
Yeah.
So if you haven't figured it out, by the way, I really like, for exams, asking you to code things that detect properties of trees. So let's go ahead and take a look at this one. Draw an example. Oh, shouldn't have closed the whiteboard. Draw an example of each of the following types of binary tree. Use a different example for each tree. Now, the reason I wanted you to use a different example is because, you know, if you didn't, I could just simply say, okay, that's a full tree, that's a complete tree, and that's a perfect tree. We're done. Right? So, that's, however, not what I want to do. Let's go ahead and move over here. And let's go and I will grab a blue pen this time. And let's think about what we want to do. So what was the first one? The first one says, let's draw a full tree. So what does it mean to be a full tree? A full tree has either all the nodes have no children or both children slots filled. So here, this is a full tree because everybody has 2 children or no children. This is a full tree. Everybody has 2 children or no children. This is not a full tree because we have a node who has 1 child. But now if we add a second node over here, it's now a full tree. Make sense to everybody? Full is pretty easy. Everybody has either 2 or no children. Okay. Now perfect is one of the cases that are actually easy to see, and you can go, yep, that's a perfect tree. That's also a perfect tree. That's also, this is not perfect yet, but as soon as I finish drawing it, that is a perfect tree. So a perfect tree relies off of needing, let's see, it relies off of needing and text. Go ahead. So if your height of the tree is h, so a perfect tree of height h, because it's always dependent on how high it is, has 2 to the h minus 1, right? That being the h here being, not actually, it's not this, okay? It's not this equation. It is, I'll be more explicit. It is 2 to the h minus 1, where h is the height, okay? Make sense to everybody? That's a perfect tree. 2 to the h minus 1 nodes, where h is the height. H is the H. Very axiomatic of me. Okay. So this is a perfect tree. If I were to add nodes all along the low level and completely fill it up, that would be another perfect tree. Everybody understand perfect? Incidentally, for a perfect tree to be perfect, right? Both your left side and your right side also have to be perfect, right? Except for the root, or they have to be, or both of them have to be completely empty. That's what it has to be. So for your, so it's a very recursive, recursive property. Now, complete is one of those ones that we can't really look at with recursion. That's one of those that actually go that because that more aligns with a queue, as we saw with a heap. So a complete tree basically is perfect on top, but then the bottom, then the bottom layer is completely filled left to right. So this is a complete tree, but this is not, because it's not filled in this left to right rule. We have a gap right here. Okay. If we add a node over here, it's again a complete tree. If on the other hand, we add a node over here, we still have this gap right over here, and it's just ugly. This ugly gap, this tree is not complete. It has not found fulfillment in its life. It does not spark joy, right? But once we add a node over here, this node is complete. It sparks joy. I know I'm a year behind on that meme, but I actually that meme's like over a year old, but I still use it. It's a good meme. All right, so really no comments in the peanut gallery. Please, it's the only way I get interaction with my students these days. I can't see your smiling faces. Okay, so any questions on complete before I move on? Either put it in the chat or expose yourself to scrutiny from your students by other students by unmuting. All right. Everybody like my costume, by the way?
Yeah, it looks good.
Pretty nice.
Yes. Looks real good.
Looks good.
All right. So maybe Laser might be convinced to dress up as Mario. Really nice. All right, so let's go ahead and look at the next example. Okay, tree operations. So making a draw tree. So this, I wrote this exam last semester, and because I'm lazy, I'm going to use it this semester too. So what we're going to do is that we are going is rather than do this, draw the binary search tree that forms after inserting these integers. Did I go over 6? Yeah, I did. The height of the tree is 1 plus the bigger of plus the height of the left or the height of the right, whichever is bigger. Okay. So for this one, the way it's going to work is I'll give you a no thank you, he says. So I give you a tree, or and I ask you to add, and I give you these nodes, and in multiple choice I ask you which one is the output. So which is the resulting tree that we get. So you won't, I don't think you will have to draw anything for this exam. Make sense? Right? It's just, here is, I've already got the trees created for you in LaTeX. So they've been rendered nicely, and you just select the correct one based off these operations. But this is actually a harder question. Most students get it right though, because it is fairly straightforward. So let's go ahead and we'll go ahead and try and annotate over here, because trying to do both of these at the same time. Mouse, scroll down a bit. Okay. And draw. So 42, right, is going to be our root node. So 10 is less than 42, so it goes to the left. 10. 42 is less, so 50 is greater than 42. That goes to the right. 12 is greater than 40. 12 is less than 42, but greater than 10. So 12 goes over here. 17 repeats the same path. 42, then 10, then 12. So it's less than 42, greater than 10, greater than 12. Hit an empty spot, so we put 17 over here. 80 is greater than 42, greater than 50, so it goes over here. Negative 12 is smaller than everything we got so far, so it goes to the left. Okay, 100 is greater than everything we've gotten so far, so it goes over here. Okay, this is really hard to draw. It's hard to do it small on this ergonomic mouse. Okay, 96. 96 is greater than all these things, but once we get 100, so less than 100, so 96 goes over here. Okay. 105 is bigger than everything else. I suddenly remembered that I'm not constrained by the page. So 86 is greater than this, less than this, less than this. 86 goes over here. Why did I do so many for this one? Right, because I expected it to be done on paper. That's why. And 72. Greater than, less than. All right, so scroll down. Using your previous answer, draw what happens when you remove the following. So let's go ahead and remove 42, then 12, then 17, then 96. So when I remove, I like to remove, if I have to remove, so if I'm removing something with two children, I always like to replace the thing I'm removing with the next in order predecessor. So in other words, the biggest thing in the left subtree. So we're going to remove 42, which means we're going to replace it, which means that we got to replace it with somebody else to keep the tree in order. So that means I go one to the left and all the way to the right. So we take 17 and we put it up here. Okay, actually we can go ahead and do the eraser over here. Okay, next step over here is that we need to remove 12. Removing something with no children is easy. You just erase it. It's only tricky when you have two children. Removing 17 now. 17 is, again, the root, which has two children. Right? So eraser again. 17. So we remove it. So what we do is that we remove the guy who's the biggest node in my left subtree. So go one to the left, all the way to the right. That means I've hit 10. So 10 goes up here, and it has one child. So this is what happens. And when you remove something with one child, it gets adopted by the parent of the thing you're removing. So you remove 17, replace it with 10. Okay, right, what we did over there was we just simply took this guy, made this 10, and said remove the 10 in my left subtree. How do I remove the 10? Well, it's got one child, so we have my parent adopted. Okay, and finally removing 96. Again, how do you remove something with one child? You just have the parent adopt it. Okay. Clear. All right, so which of the following is a pre-order traversal of a binary tree?
Someone asked in the comments, how do you remove something with two children?
All right, so to go over that again, to remove something with two children, you always, to remove something with two children, right? You always go for the next in order predecessor or the next in order successor. So let's go ahead and drag over here. So what we do is that we have, say, our, let's see, do we have any other choices? Rainbow pen, sure. We have our node over here. And so let's assume this is a binary, that this is a binary search tree. So everything is sorted, right? What we want to do is that we want, and let's go ahead and say this is A, and this is just labels, okay? And X, okay? These are just labels. I don't really care about the right subtree so much, so I'm just going to draw a little bit over there. Okay, so when you remove anything that has two children, it doesn't matter where this is. So for instance, A could be the child of something else, right? So say I want to remove A over here. So the way you remove it, in order to maintain, you can't just randomly grab any other node and put it there, because if we grab this node and put it over, if we grab this node over here and put it over here and replace it with A, well, while it's easy to remove that, the issue is that we end up basically putting things out of order because we just moved the smallest thing into the root position, which means that everything to the left is bigger than it. Yeah. Right? Because that might be 5 and we're replacing it with -1, and this would be like 4. And that could be a big issue there, right? If we move -1 up there. So you can't just take any random thing. The only things that you can replace this with to keep it in order are the next in order predecessor and the next in order successor. In other words, the thing that is the biggest thing that is smallest than this, or the smallest thing that is bigger than this. Doesn't really matter which one, but I like to do the biggest thing that is smaller. Now, everything that is smaller is right here in the left subtree. Okay? So everything that's smaller right here, left subtree. Except for this guy, he's not part of the left subtree, even though he was in my badly drawn circle. Okay, so now the biggest thing in this thing again, right? The biggest thing over here is the thing that's all the way to the right, right? Because let's think about it logically. If the biggest thing was to the left of something in here, it would mean it was smaller than something, so we would want the thing that was its parent, right? So so what we do to find it is that we take one step to the left, we zig, right? We take one step to the left to get into the left subtree, and then we zag as hard as possible. We go all the way to the right as far as we can. Doesn't matter if this is if there's no other right subtree children, that's fine. But here's the thing. Once we go all the way to the right, okay? Once we go all the way to the right, we are guaranteed to be in one of two scenarios, okay? Which is that the node all the way to the right is either a leaf node with no children, or it has one child, or in other words, was one subtree, which is fair. And both those cases are super easy to deal with, right? So what we do in those cases is that we would take we'd take A and replace it with X, right? Since that's the biggest thing in the smallest subtree. So we just basically take this information and copy it over here. And then we would delete this extraneous X, the old X's old position, okay? So how do you delete X's old position now? Well, if you're just one child, boop, 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 like that, just erase it. You just return null to its parents and say, replace me, and tell this guy, hey, replace my kid with null. If on the other hand, you have this subtree over here, you have some children, you're guaranteed not to have any over here, because if you did, those would be bigger than you, and that would have been your target. So if this is the case over here on the left, what we would do is say, hey, parent, you, adopt my kids. Thank you. Okay, and so you do this. And now basically your tree, your subtree gets promoted over here. So basically, it comes down to what you do is you copy this over here. You copy your in-order predecessor, and removing your in-order predecessor basically means now we're only removing a node with 1 or 0 children, which is easier than removing a node with 2 children. So we reduce it to an easier case. Okay. So let's go ahead and go on to the next one. I don't want these. So, which of the following is the pre-order traversal of a tree with subtrees left and right? So pre-order means do the root first before we do everything else. So in that case, it is we handle the root node, then we go left, then we go right. This is opposed to in order, which is we go left, then we handle the root, then we go to the right. So basically pre-order says, run whatever I need to on myself first, then run the pre-order traversal on my left, then run the pre-order traversal on my right. Post order, on the other hand, says, hey, I'm going to do myself last. So we do my left, then we do my right subtree, then I do myself. All right, heaps. I'm not even sure if I put them on the exam for this time around, but that's okay. Hopefully you all watched your lectures on heaps, even though there wasn't associated homework with it. So heaps, right? They are the backbone for priority queues. A min heap basically says, let's always keep the smallest thing in the root node, and this is a recursive process. Also, we always keep it in the structure of a complete tree. So let's go ahead and draw this sucker. Format, huge line width, big pen, purple ink. So first things first, we draw, oh, that's terrible. First things first, 8 goes in first. Then then we need to insert 10. Now, when we're inserting into a min heap, we always insert in the next position in a complete tree. So we put 10 here. The smallest thing is still the root. So, and that process holds recursively, so we don't need to adjust at all. Okay, next is 10. 10, sorry, we did 10. Next would be 50. So we just put 50 over here. No problem. No problems yet. Now we put in 20. No problems yet. Again, I'm just inserting them in the next place that a node in a complete tree would go. Next, we put in 1. And now we have some issues. So what you do whenever you insert something is you go, am I smaller than my parent? If yes, swap with my parent. Continue until this is no longer the case. So 1 is smaller than 10. So that's fairly easy to rectify. We just swap them, which I can do by just simply, of course, just erasing a 0 and drawing a 0. And now again, we ask the same question with 1 and 8. Is 1 smaller than 8? Yes, it is. So we swap 1 and 8. Okay, now let's go ahead and insert 4 into this tree. 4 is greater than 50, so we swap 4 and 50. All right. And finally, I really wish I had my pen because this would have been so much easier to do. Finally, we answer, and then 4 is larger than 1, so it stops swapping. Finally, we put in 3. 3 and 4 swap with each other. So the way I like to think of it is that we put an item in at the next place in the heap, and the smaller items always bubble to the top, while the heavier items bubble to the bottom. Sink to the bottom. So that's our answer for that one. Now, using the heap we drew above, love making you do the work there. Draw the heap after removing an element twice. So how do you remove an element from the, I say an element, but you always remove from the root of a heap, essentially. at least in this class. So so what we would be doing is that we remove this guy, but when we remove an item, we have to replace it because it needs to be a complete tree. So what we do is that when we remove an element, we always replace it with the last item because removing that item is and putting it at the top is the easiest, right? So when we remove an item, we take the one from the bottom and put it at top. But however, the tree is now out of order, right? Or the heap is now out of order. The smallest item is no longer at the top of the heap. So what we have to do is we have to fix that by having the heavier item sink. So which way is it going to sink? Well, 4 is less than 8, so we don't want 8 to rise up. But 4 is greater than 3. 3 is less than 4. So we want 4 to swap. In this case, with 3. We swap with the smallest child. Okay, if we're bigger than one of our child, we swap with the smallest child. Now 4 is smaller than 50, and we've got bedrock on the other side, so we're not going to sink any further. Now to remove 3, what we do is we remove this guy, replace it with, we remove 50, right? Because we got to remove 2 items. That was what the question said, remove an element twice. So 50. 50 is greater than both of its children, so we swap with the smaller child. So 4 gets swapped with 50. And 50 has hit bedrock, so there's nothing to swap with, so now we're done. Notice the 2 gaps, and also notice that basically the recursive nature of the heap, which is that each side of the heap is also a heap in itself. Okay, heaps are used for priority queues. So this is what we use for the next part, which is Huffman coding, which I don't know if I put on this exam or not, to be honest. But how many of you had trouble with this one? Because this was the, what?
I did.
Okay, so this was a topic in the heaps section, but it is basically a basic form of compression. So let's go ahead and think about what we've got here. So move. So draw the text for these symbols. Okay, so let's go ahead. We've got A is, so let's go ahead and put these in order. A is 50. Well, actually, let's put them in just the order we have. So forget what the weights for a second. So X is the smallest. So we're going to put them in order in a priority queue, then L, then P, then A, then E, right? E has a frequency of 60, A has a frequency. So you put them in order like this, right? That makes sense why it's in order like that. The smallest thing is first, followed by the next smallest thing, followed by the next smallest thing, followed by the next smallest thing.
I had a question. So when you remove from the heap, you remove the root first? Is that how it was?
Yes.
Okay.
Or which ends up being the front thing in a queue. So now what we do here is that to draw a Huffman tree is that we have X and L as our first 2 things. So we go ahead and we remove X and L from the heap, create a tree with a node as their parents and put them in. Okay. So now this now what the weight of this guy is 1 plus 20 or 21, right? It has a combined weight of 21, right? So we removed X and L. So P has a weight of 20, A has a weight of 50, so P has a weight of 40, not 20. A has a weight of 50, E has a weight of 60, L has a weight of 21, so we put it into the priority queue, but it's a priority queue, so it doesn't go on the end. It goes to the beginning here because it is the smallest thing. Make sense? The smallest thing. Now we just repeat. With this, we simply remove the smallest thing in the queue, put that on the left, and put the next smallest thing on the right, which would be our P. I don't know why I put a 4 there. So 21, and so again, they get connected by a node. So the first thing in the queue goes on the left, the second thing in the queue goes on the right. So now they have a combined weight, or rather this would have been XL, not L, it's been XL. So XL and P will have a combined weight of 61. Combined weight of 61 over here. So now again, we repeat A and E. Let's see. A and E are 50 and 60 respectively, and we'll combine. And so we'll move them from the queue, and we draw a node over here, and so A and E. A was smaller, so it goes on the left. We have E, which goes on the right, and we connect them. And then we would put this, and then we put A and E into the queue, which has a combined weight of 110. So it goes on the end of the queue. Now we have XLP and A and E, and they get connected like this. And so then we're done. Okay, so now how do we use this? Well, all the lefts get marked with zeros. All the rights get marked with ones. And so we can encode like this. So the encoding of A would be 1, 0. Sorry. The encoding of A would be 1, 0. The encoding of P is 0, 1. 1, 0, 0, 1, 0, 1. The encoding of L is 0, 0, 1. And the encoding of E is 1, 1. So encoding Apple gets us this, which you can just simply keep the spaces in, but that's fine. All right. I don't think this is on the exam, but it would be on the final. So I'm going to go and move on to the coding portion, because we definitely have coding portion on the exam. And I'm sure that's where you're most interested. The coding isn't nearly as hard as last time, but it is, how do I put it? It is, it's useful. So what am I doing here? I need to remove the annotation. That was a lot of work for my wrist. All right. So size of a tree. You write a method which, given the root of a tree or subtree, computes and returns the number of nodes in that tree or subtree. You may not use the size method. Forget that it even existed to begin with. This is a great coding golf question. I'm just going to go ahead and so I'm going to go ahead and boot up IntelliJ. I'm not going to use a tree. I'm just going to have the node class. I'm just going to make a node class for this. Okay. And what because that's all I really need for testing purposes. In fact, I'm probably not going to test it much. It's more what I need for it to compile. But you might want to think about making yourself a more robust testing structure for yourself. So having a working binary search tree for the exam, so that if you want to do tests, which you don't need. So I'm going to call this tree exam questions. And all I need to run it is, or all I need it for it to compile is I need to make the node class. So private static class node, which means that I can, and the static enables it to exist without the, it enables it to exist without having to worry, without making a tree exam question class. So node E, and yeah, I'll have to put in a generic somewhere. So private static class E item, node E left, node E right, public, and let's just create the constructor, public node E item this dot item equals item. All right, so let's go ahead and make a public static double, sorry, public static int static E int size given a node E root. All right, I'm going to go ahead and quash this error by returning -1, which is, of course, everybody knows an acceptable answer for a tree's size. I did not mean to hit shift 5 times. This keyboard is, again, just takes some getting used to. All right, so to compute the size for the sucker, it's not too bad. Really, the size, so let's think about this. If I don't exist, so if root equals a null, that's a base case right there. Always identify your base case first. And the easiest base case is asking yourself, do I exist? Right? So for humans, that's kind of a nonsensical question, or possibly one of the most existential questions we can get. But for a root, that's fairly easy to answer. If it's null, return 0, because obviously if the tree doesn't exist, its size is 0. Otherwise, I exist. So yeah, that's a great. So otherwise, I can just simply say int. So I'm going to do this like really large, and then I'm going to like shorten it immensely. So my size is 1, obviously, right? Because I exist, therefore, you know. Now, on the other hand, I need to figure, I possibly have a left child and a right child. I'm not going to bother checking to see if they exist. They can figure that out for themselves. So they can experience their own existential dread. So if left side, so my left size is going to be equal to size root dot left, and my right side, well, its size is going to be size root dot right, and the total size of this tree or subtree is going to be equal to not -1, but my, I'll go ahead and do it in order. My size plus, sorry, left size plus my size plus right size. Okay, so let's work on shortening this, because this is completely correct. I can just simply do this to shorten it. I can just do the recursive call right here in the return statement. No problems with that. And that shortens it. Okay. And then we can do my size. Well, there's no need for the variable. I can just simply, now that I understand the problem, I can just simply replace it with 1. And so we can get down to, yeah, 1, 2, 3, 4, 5, 6 lines. I can get down even shorter by removing the if statement if I wanted to. I do, and using a ternary statement, but I don't suggest doing that, which is as follows: root, because it makes it hard to read. Root equals null. Question mark 0 colon there. And now we've got it down to that. So what did I just do there? That is a ternary statement. It is horrible. You should never use it because they're unreadable. But essentially, it's an inline if-else statement saying, hey, if it's true, do the thing before the colon. If it's false, do the thing after the colon. Make sense to everybody? It looks really neat when you do it, but honestly, it's hard to read, and readability is everything in my book, so don't do that. Much easier to do this. Okay, now let's go to the next question. You will have 2 tree questions to code, by the way. Or rather, it's one question split up into 2 parts, and you'll call the first part in the second part because that helps break it down. So write a method which, given a tree, returns whether the tree is a full tree, right? Has one child. In other words, does every node have 0 children or 2 children? So it's slightly different than recursive traversal methods we've tried so far, right? And I need to remember why, because I haven't touched this problem in like, since summer, I guess. All right. Let's go ahead and paste it over here into IntelliJ. And let's go ahead and help our poor copy pasting job from a PDF. Boolean is full. So I'm going to go ahead and call this root. Doesn't matter. OK. So default is probably going to be wrong. I'm going to just assume that it's that it's true. OK, I'm just going to, I got to put something there. OK, so I'm just going to put return true. Now, with regards to figuring out whether this thing is full or not, so let's go ahead and first ask ourselves the existential question, right? Which is, do I exist? So just work through your base cases as easily as possible. Do I exist? If root equals null is almost always the right question to start with. If the root of this tree is null, honestly, I don't know what to do there. I'm going to assume, though, returning true. It may be a completely, depending on how we write it, it may be a completely unnecessary statement. Return true. True. Null is not true. OK, so I do exist. Now, what in the world do I need to do? Well, being full does actually depend on whether or not I have left child or right child, right? So, so let's think about base cases, right? When do I know I can return false? I can return false when I have 1 child, okay? So if root.left equals null, and, which in this case is more of a but root.right is not equal to null. In other words, it exists. And I could make an or statement there with the other condition, but honestly, it's just, again, readability is king in problems. Yep. OK, and now copy this guy. Much easier to do it this way when you're on a computer. So let's copy this guy, do root dot, and let's just switch this. This isn't, if we have a left child, but not a right child, we are not full. So return false, right? It doesn't matter what else goes on in the tree, on our subtrees or in our parents, it doesn't matter. It's not a full tree because we found a case where we have 1 left child, but no right child, where we just have 1 child, okay? So let's go ahead and now, so if we're in any of these cases, by the way, and we don't need an else because of the return statements. The return statements just kind of act as automatically making it an else statement for us. So now we're in the case where we have either 2 children or no children. You know what? Let's go ahead and just handle that case of having no children. So if I have no children, then that's full. So I'm going to go ahead and return true. On a roll today, Andrew. Return. OK. So now if we're in this case now, we are in the case where we have two children. So, and yeah, readability, let's go ahead and make it else ifs. Just for readability's sake. So now we're in the case where we have two children. Now, if we have two children, I can't just return true because I have to check if my children are full, right? So all I'll do here is I'll do the recursive case, which is return is full, root.left, and is full, root.right. Now this first thing I think then becomes unnecessary except for the topmost root, so I'm going to keep it in. But now this condition, because we've got an else down here, is perfectly fine. So over here, I'm just simply saying, hey, okay, no children, great, full. One child on either side, but no child on the other, turn false. Okay, now where is my error? Do I have an error? Okay. Oh, that was embarrassing. Okay, so now return is full on root.left and root.right. If I have two children right, I'm going to go check if the left and right are full. All right, so now we have a turbocharged extra credit question on this one. Definitely harder than anything I would ask on the exam, by the way. Okay. This is about equal of the difficulty I'd ask on the exam. This is about tougher than I'd ask on the exam, which is check if the structure of two trees and the contents of these two trees are exactly the same. They're equals if and only if the structure is the same and the contents are the same. So they have to be shaped exactly the same and have the same numbers or items or whatever they are. Right? So let's go ahead and paste that in there. Correct the pasting, right? Put in a generic because I do need to put that in here. Public static Boolean equals. Okay, we've got this. Okay, so now we are going to assume that they are, you know what, I'm going to put return true again just to simply quash the error. So let's go ahead and talk about base cases. So first, we need to ask them both if they exist. And it will look very similar to these conditions we had over here, right? Because we can't just ask if one of them exists. We ask them if both of them exist. But that actually produces a lot of useful cases for us. Like, for instance, if tree A, if they're both null, then obviously they're equal. Make sense? If they're both null, then we are in good shape because they're equal. Else, if one of them is equal but the other is not, right? If one of them exists but the other does not, then they can't be equal because something can't equal nothing, right? If you're something, you're not nothing, right? There's your inspirational quote for the day. It's a crappy one, but hey, on this rainy day, we'll take it. Okay, so, and the other way around, right? If A doesn't exist, but B does, they ain't equal, so return false. Okay, so that leaves us with one possibility with an else statement over here. Okay, and I will go ahead and I'll keep that there, but then I'll erase it. So now actually is where we like hit the recursive case and we're like, what do we do? But actually most of the time getting the base case is the hardest part. Well, okay, well, I exist. So the question first is we need to check our data to make sure we match. So first thing let's do is that if tree A dot item dot equals tree B dot item, right? We want to check to make sure the data matches in those things, right? So let's go ahead and switch it over and say, let's say if they do not match, return false, because of course, we can just stop there. Because if the items don't match, then that doesn't matter. We don't have to worry about the structure. But if they do match, then well, those are the same. So let's check the structure, which is that let's go at, well, we exist, but we basically need the way we would check our structure and say, hey, are our left subtrees equal and our right subtrees equal? So return is equal, or sorry, returns equals tree A dot left, tree B dot left, and equals, everything okay?
Molly found leftover pizza.
Molly found leftover pizza. The cat found leftover pizza. The animals believe that the toddler is the greatest thing to ever happen to them while he's not harassing them. Because he leaves all sorts of treasures all over the place. Now we can remove this, and we're good to go. So you see that? How'd that work? If it's true, so again, what we do is that we basically say, hey, what are the obvious cases? Basically, okay, nothing matches. Sorry, if they're both nothing, then they're equal, so return true. If we have one on one side but nothing on the other, then they're obviously not equal, so we return false. Then we check the data inside of them. If they don't match, that's false. Otherwise, well, they match entirely, so now we just need to pass the problem along to our children. So each of us, we're going to check the left subtree, then we're going to, well, undecided, you check the left subtree, then you check the right subtree, right? So there you go. And that's how you do that one. Now, let's go ahead and look at the most common question. This will basically be there will always be some variation of this problem for map. So, which given a string, count how many times it occurs. So, or count each time the character occurs. This is actually a fairly straightforward one, and there's lots of ways to do this. Lots and lots and lots of ways. But I'm going to start with but because I like to do that, I'd like to start with the most obvious ways to do it. So public static, return a map of the characters to integers. And let's basically count how many times each character occurs in this word. So let's go ahead and create our map. So map is equal to new hash map. I'm lazy, so I'm just going to hit copy on that, paste over here, hash map. Get to know your keyboard shortcuts really well. The less you have to pick up the mouse, the quicker you're going to move. Okay, so on Windows, hitting Control and left and right really speeds things up because you're jumping basically between white space and punctuation there. And then you can combine it with Shift to select things. So really knowing things like that. I don't know what the equivalent is on a Mac, but it's useful. There's all sorts of shortcuts. Some are universal, some are application specific, such as, let's see, Control Shift. I don't know. Yeah, Control Shift up and down to make stuff swap. So like this for IntelliJ, that's really cool. Okay, so there's all sorts of keyboard shortcuts. You want to look for really common operations that really need to be done. So, okay, we've created a new hash map. And even though it's empty right now, we're going to return it at the end of the program. So let's put it there. Again, note, we always want to make sure we don't get our compilation errors because we always want to have our code in runnable and testable state. So let's do a for loop. I'm going to do a for each loop because I like that. So for car letter in word, but we can't just do it like that for a string. We have to do to car array, boom, boom. Okay, so for every letter in that array, let's go ahead, or in that string, let's go ahead and ask, have we seen it before? Have we not seen it yet? If letter, I was about to write not in, but that's how you do it in Python. So map.contains key letter. So do we have that? Have we seen this yet? Is this a thing? If map does not contain this key yet. well, then this is the first time we've seen this letter. So map.put one, or rather letter, and we've seen it once so far. Otherwise, we have seen it before. So what we need to do is get int previous number of times we've seen it is equal to the previous number of times we've seen it is equal to map.get the letter. In other words, get how many times I've seen it before, and then map.put letter prev plus 1, or previous plus 1, because I was pedantic and wrote it all the way out. So basically get the number of times I've seen it before, add 1 to it, and put it back in the map. Then we're done. That's really it. It always works in this kind of format when you're just counting stuff like this, which is really common when you're counting things and you don't know how many things you're counting, right? If you knew how many things you were counting, like tell me how many E's are in here, then you could just create a variable, but you don't know how many E's there are. So you have to have something that will hold variables as you do it. Now, that being said, if you're doing the other way you can do it, which isn't if you don't use a map or anything, but you got to use a map for this one. But the way you would do it if you did not have access to maps and stuff like that would be to do it would be to create an array and have and basically map things to the array using the ASCII character code. So if it was at array 97, the number at array 97 index represents the number of A's you have. There's a couple ways we can shorten this. For instance, I could remove the else. Could remove the else over here. And then just simply put this in as 0. So if it doesn't have it, say create a slot for it, then no matter what, you know it's there, so you can do the get operation and then put one in. We can also just, remove the previous, put this in, boom. Okay, which is a bit harder to read again. There's also, I think, a map dot, is there a get or default, which is real, and that really speeds it up. So map.put get or default actually. So this really speeds it up, and this is basically the one-line solution to it. So what does get or default do? It's a special function. Obviously, it's kind of a get function because you're getting a letter. But how does this work? Well, get or default says if it doesn't exist, default to something else. All right. So if this letter isn't there, instead of crashing and burning on me, how does the get operation work on a map if you don't have if it doesn't exist? So if you try to get question mark and you haven't seen a question mark at all, you'll get a key error or key exception, right? But what we could do is that we can use get or default to say, wait, if you don't see it, don't crash and burn. Instead, just give me this instead. And the computer will do fine. So if you haven't seen it yet, this becomes a 0. And then you add 1 to it, so it becomes a 1. And there you go.
Professor Rosen, I had a question.
Yes.
If you try and get a key that doesn't exist, doesn't it return null? I think no when I read it in the notes.
I forget how it works. And
Otherwise,
I switch between, I switch between Python and Java so much. Java, what is I can't even remember the name for the Java here. Let me go ahead and check on Java command line. So yeah, Java command line. Oh no, Java REPL. How do I use the Java REPL? Forget. J shell, that was it. Okay. Yeah, I'm sorry. I've been working in Python, so I might have told you a load of lies. But the point still, it says it would still crash and burn with just a get operation. So let's run J shell. So map integer equals new hash map. Okay, error. Oh, I didn't give it a variable name. Map. Boom. Okay, we've created our map. Map.get 0. Okay, yeah, you're right, Andrew. We would get null. Yeah, so total lie there. We'd get null, but it would still crash and burn anyway, right? So here, because we would get, if we just had a get, we would get null back, and null plus 1 is error, right? So this would give us 0 back instead of null. Yeah, in Python, so yeah, I was just thinking in Python. This is the issue when you teach two languages at the same time and you're teaching some similar topics at the same time. You sometimes get them mixed up. It happens. Okay. Also be relieved that I'm still making mistakes at this point. How do I quit out of this? Seriously? Boo. You know what? I'm
It's
just
just
gonna,
Control C.
nah, because
I think it's /quit.
that's right. That's right.
A /, I think. Nope.
/help. Help. /exit. There we go. Okay, yeah, in Python, okay, if you have a dictionary, which is the same thing as a hash map, and you try to get a key that doesn't exist, you get an error. There we go. Okay, so that's where I was getting confused. That is, again, the issue when you know multiple languages. So for the sake of time, I'm going to skip the last extra credit question because there won't be an equivalent on the exam. Again, but that's just simply categorization, which hopefully you've had plenty of practice by this point on, which means now I have to store previous session. Okay. Try again. Boo. Boo, I say. Okay. Give me 1 second to get it, to pull it up on my computer. Profa. Teaching. Destruct. All right, so now I'll just go over the last theory questions. You'll have some. So what are collisions in hash table? Why do they occur? And how are they handled? Okay. So any takers for this one? I mean, I've been done this whole exam. I think it's only fair that you answer one.
When more than one item has the same hash key, and it depends on the implementation how they're handled, but if the hash tables are made with array lists, they just extend the length of the list. And if they're handled with linked lists, they just add another node to the list.
Sorry? Well, not if they're handled with array, there really isn't so much a handling with array lists with this one. What you do is if the hash table fills up, you extend it like an array list. You have two primary methods of handling collisions. But yes, collisions occur when you've got two things that are trying to get into the same space. And this happens because we don't have an infinite number of space, but we have an infinite number of keys. Infinite number of possible keys. So of course, you might get a conflict where two things try to go into the same space. So the way you handle there are two strategies for handling it. One is open addressing, which just simply says, okay, my space is taken. I'm going to go to the next space, the next available space. Now, what the next available space is depends on the definition of next you're using. In linear probing, that means literally the next available one linearly searching that you can find. right? So if I can't find it at index, I look at index +1, then look at index +2, then index +3, then index +4 until I find an empty spot. If you're using quadratic probing, then you would use, you're looking at index +1 squared, index +2 squared, index +3 squared, index +4 squared until you find an empty spot. That has the advantage of spacing them further out, but it's slightly more expensive because you're not doing an addition operation anymore. You're doing an addition and a multiplication operation to figure that out, right? You're the whole squaring it. Now, the other way to do it is, as you mentioned, which is handling it with a linked list, which is the bucket method or the chaining method, which is simply says, rather than having a slot being able to hold one item, we are going to hold, we're going to have that slot be a list. And so if that slot is taken, then we just append it to the end of that list because that helps. Makes sense, right? Expensive, just throw it on the end. And then when we're looking for the item, we know to look in that slot specifically, and then we iterate through the list. And so long as things are evenly distributed, then on average, it will still be constant time. There's also kind of different strategies such as cuckoo hashing, which is one of my friend's favorite, which just simply says, hey, you're in my spot. Get out of my spot. After cuckoos and kicking, and cuckoos have a penchant for kicking other birds out of the nest. So, and so then it becomes the other item's responsibility to find its spot, and it might kick other people out. It's pretty funny to work, but it works. So there's also double hashing, which is, okay, if I can't find the spot, use the second hash function to try to calculate my spot. But open addressing is really the one that we test you on the final exam. Okay. So now, what is the worst case insertion and deletion runtime algorithms in a binary search tree and why? Okay, what's the worst runtime for this and why? What's the average case runtime for these?
Log base 2 of n? Or?
Yep, average base is log base to event. What's the worst case runtime for insertion and deletion for a binary search tree?
Isn't it just log base to event?
That's average. Let me give you, it's log base to event if it's balanced. What if it's unbalanced? How bad can it be?
Then n, I guess.
Yes. So if we add items, like if we were to, so say I were to hit the home key, I were to insert things in order of the home key on your keyboard. In other words, that's a terrible one. A, S, D, F, right? That is essentially a linked list there. Just it's a fancy way of doing a linked list with more wasted space. Or if you were to enter items in order, you might get 1, 2, 3, 4, 5, 6. Or if you were to do the quick brown fox jumps over the lazy dog, you'd actually get an unbalanced tree too. And in unbalanced trees, each decision you're making isn't reducing your search space by half. It's reducing it by like 1 or 2, which is super inefficient. So it would be O of n. Now, the key to fixing this is a balanced binary search tree, which is covered in chapter 9 of the book. And because of every semester I try to think maybe is there enough time to cover that, but this is not the semester for that, to try to cover more than I normally cover. But chapter 9 does balance binary search trees such as red-black trees, 2-3 trees. ABL trees are the kind of classic. And what they all say is that if you've been inserting things and keeping it balanced, if you insert an item and that makes the balanced tree unbalanced, right? Well, inserting would have taken log n time, right? So that's already so we already have that cost. But balancing actually takes also log n time. If it was balanced and suddenly you just made it unbalanced, only just made it unbalanced, it takes log n time to rebalance it. So log n plus log n, which is still log n. So, and the same thing is true for removal. So that's how balanced binary search trees have a worst case runtime of log base 2 of n, well, or log n, because in the case of 2-3 trees, they have more than 2 branches. They can have 2 or 3. And 2-3-4 trees have 2, 3, or 4 branches. So that makes the runtime slightly more complicated, but essentially faster, actually, because there's more branches, and that cuts out more. All right, so that is that for the exam review, and I finished right on the dot.